When we're doing graph puzzles, we really have to be extra careful about points of discontinuity. Now, these could be vertical asymptotes, where the divide by zero doesn't cancel. It could be a hole in the graph where the factors do cancel. And they can be breaks in the graph where the left-hand limit is not equal to the right-hand limit. So these are some summaries here that we should consider. Uh, non-differentiable points as well. I haven't added in here, but these might be things where it is not smooth and continuous. So vertical asymptotes, holes, where the left-hand limits and the right-hand limits don't equal each other, where we get jump discontinuities. So these are some things that we should be conscious of. So example one, we've been given information about the function, the derivative function, and the second derivative. And it is a continuous and differentiable function whose domain is from 0 to infinity. Now, the fact it's differentiable is really important because what it means is that differentiable means it is smooth and continuous. Okay, so if we know that something is differentiable, we know that it's smooth and continuous, and the derivative is defined for all values of x. So that's one thing. The domain is from 0 to infinity, so we don't have anything happening to the left of 0. And it says here that as we approach 0 from the positive side or the right-hand side, we are going to negative infinity. So this means that we have a vertical asymptote. Okay, so I'm going to draw my vertical asymptote at 0, and we know that from the right-hand side, it's pointing down. Now I'm going to look at the bottom term here as well, because this gives me the horizontal asymptote, okay, endpoint behavior, as x goes to positive infinity. So what ends up happening is, as x goes to positive infinity, it is going to have a horizontal asymptote at 0. So looking at rest of this information, looks like we have at f of 1, it's equal to 0. So I plotted that point at x is 0, at x is 1, y is 0. And I want to make particular note that notice that the graph's going to cross the horizontal asymptote. Now, although you cannot cross a vertical asymptote, you can cross a horizontal asymptote. In this graph, we will cross a horizontal asymptote. So for x is less than, for x is less than 1, so on the left side of 1 to the asymptote is f of x is less than 0. So it's going down. That confirms the fact that it's going down to the vertical asymptote. And from x is bigger than 1, it's going to be above the x-axis. So it's not going to cross the x-axis again. So after we cross the x-axis at x equals 1, we're going to stay above the x-axis. The second part is we're being given information about the derivative. So f prime of 2 is equal to 0. So I'm going to start a slope chart here. So at f prime of 2, we're going to have a 0 value. And it tells us that it's going to be positive, or f prime is greater than 0 when it's less than 2. So on this side, it's going to be positive going up like this. It's going to go across like this. And then for x is bigger than 2, the f prime is less than 0. Okay, so that's going to give us, this one here on the right is going to give us negative slope on this side. So we know that we have a maximum point at x equals 2. So maybe some maximum point up here. We don't know exactly where it is, but we know we have a maximum happening at x equals 2. So the second derivative tells us concavity. And we're told that f double prime of 3 is equal to 0. So that's a potential point of inflection. So we know we have a 0 concavity here. And so between 0 and 3, if we take a look at this, it says between less than 3, we have the second derivative is negative or less than 0. So that means we have negative concavity. So negative concavity means it's going to be concave down. And our slope chart seems to support it, and our function, what we've drawn so far, seems to support it. In fact, we probably can draw this through here like this, and it's going to this point. And at 3, it's equal to 0, and on the right side of 3, the second derivative is positive, so we know we have concave up. So at x equals 3, we have this point which is going to change concavity. So from concave down, we're going to now go to concave up, and it's going to follow that horizontal asymptote. Okay, so this is a continuous function, and it's going to look like this. And this now then satisfies all those conditions, and a number of those conditions are redundant. It means that one condition will confirm the other condition. For example, concave down can be shown with the concavity or the slope chart.